So let's do a quick overview of the VSEPR theory. VSEPR is valence shell electron pair repulsion, and what it allows us to do is predict the three-dimensional shapes of molecules. And if you look at those terms involved, we're looking at the valence electrons, or the electrons in the highest occupied energy level. They're always going to come in pairs in covalent compounds, and because they're like charged, they push away from each other, and it's the repulsion of those valence electrons around central atoms in a molecule that determine three-dimensional shapes of the molecules. And we're going to be looking at the bonding or shared pairs and how they behave, and the non-bonding pairs or the unshared pairs and how they behave to make three-dimensional shapes. An overview of all of the VSEPR shapes or the molecular geometries are listed on this diagram. The left column there, we have what are called electron domains, and those are regions of repulsion. They could be shared pairs, they could be unshared pairs, and the other thing to keep in mind is that double bonds act as a single repulsion area or a single electron domain, as does a triple bond. There are a lot of crazy shapes going on here. For the purposes of our introduction, we're really just going to be focusing on 2, 3, or 4 electron domains and the 5 shapes that can result from those scenarios. The 5 and 6 electron domains are elements that can expand their octet, that can form more than 4 bonds, that can have more than 4 electron domains around their central atom. All right, so starting with 2 electron domains. If you have identified 2 electron domains, then your molecule is going to be linear. Both the electron geometry and the molecular shape are going to be the same because for the molecules we'll look at, there'll be no unshared pairs of electrons. So again, when we say 2 electron domains, with respect to, say, that central atom on the HCN, you have 1 electron domain there, then the triple bond is a single electron domain. And those 2 regions of electrons will push away from each other to get as far as they can get in three-dimensional space, which is 180 degrees. If we're talking about 3 electron domains, then we have 2 possibilities. Either all of our electron domains are bonds, or we have a mix of bonding and non-bonding pairs of electrons. If all 3 of your electrons are bonds, then you're looking at the carbonate molecule down there on the left, and your electron geometry and your molecular shape will match. They will be trigonal planar. This actually holds up across all of the shapes that we're going to look at. If you have the same number of sets of bonds as you do electron domains, then both your electron geometry and your molecular shape will be the same. If we're looking over here at the ozone molecule, the O3, we have 3 electron domains. We have the single bond, we have the double bond, and then we have the unshared pair of electrons. So even though you only have 2 sets of bonds, they can't push to be 180 degrees away because there's that unshared pair of electrons that's going to take up repulsion space, and they're going to force it into that trigonal planar shape with respect to the electrons, but we only look at bonds when we look at molecular shape. And so your molecule here is going to be bent. And because unshared pairs of electrons push with more force than bonding pairs, rather than the standard 120 degrees in the trigonal planar molecule, the bent shape that is the result of 3 electron domains is going to have slightly less than 120 degrees as that bonding for that bond angle, because non-bonding pairs push with more force than bonding pairs. Now our last one we'll look at is 4 electron domains. The electron geometry for 4 electron domains is tetrahedral. Again, if there's no unshared pairs of electrons, then your molecular shape is also tetrahedral. So we look at the CH4 there. The convention with the lines and the triangles is those are supposed to represent the three-dimensional shape, with one of them popping out of the screen, one of them going behind the screen. So those 3 hydrogens in the bottom make a bit of a tripod. And there's 109.5 degrees in between all of those sets of bonds. Any 2 hydrogens will be 109.5 across. Again, 4 electron domains are the 4 bonds. If we look at the ammonia molecule NH3, it has a tetrahedral arrangement of electrons, but it has one unbonded pair of electrons, so we only look at the bonds. And that unbonded pair is going to force those hydrogens down into a pyramid shape. So you're still going to have that tripod of the tetrahedral, you're just not going to have the thing coming out of the top. Again, non-bonding pairs of electrons push with more force, so instead of the 109.5 degree that you would expect, you're going to get a little bit less of an angle. So in between any two sets of hydrogens, it'll be 107. If you have 2 unshared pairs of electrons, like in your water molecule there, then you're going to have a bent shape. So it's one kind of angle of the tetrahedral is all you get, and those 2 unshared pairs of electrons squish that 107 down even a little bit more, so the bond angle there is 105. So that's 1 electron or 2 electron domains, 3 electron domains, 4 electron domains, and the shapes that you can get from that. You might also look at this in terms of types or number of bonds. If there are 4 bonds in your compound, for the ones that we're going to be looking at, then you are going to have a tetrahedral molecule. If you have 3 bonds, then you're looking for an unshared pair of electrons on your central atom. If there's an unshared pair, you've got pyramidal. If there's no unshared pairs of electrons, those 3 sets of bonds are going to stretch out into that trigonal planar arrangement. And if you have 2 sets of bonds, 2 unshared pairs of electrons are going to put you in the bent shape at that 105 degree angle. 1 unshared pair of electrons is going to push you into that bent shape from the trigonal planar, so slightly less than 120 degrees. And no unshared pairs of electrons on 2 sets of bonds is going to get you a linear shape. So there's really 2 ways to look at this. How many bonds do you have, and then are there unshared pairs or not? Or you can look at electron domains and how the number of bonds reflects with the electron domains. Either of those things should help you figure out a 3-dimensional shape from a dot structure, and that's the overview of VSEPR, or valence shell electron pair repulsion theory.